Perform quantitative risk analysis is the process of numerically analyzing the combined effect of identified individual project risks and other sources of uncertainty on the overall project objectives. Some of the project documents that we may look at as part of this process could include the cost and schedule forecasts. By looking at predictions as to cost and schedule performance, we can do a quantitative analysis to determine the confidence level associated with achieving the targets that we have set for ourselves. This could be represented as saying we have an 85% level of confidence that we will be able to achieve within our original cost baseline. Representations of uncertainty that we may use could include probabilistic distributions. Some of the common distributions that we may select are triangular, normal, log normal, beta, uniform, and discrete. The distributions are typically used for the overall project risk. However, it could be used for individual risk events when necessary. Data analysis could include a sensitivity analysis. This is where we compare variables against one another to determine which ones have the greatest potential impact on the project. This is typically shown as a tornado diagram, with the largest range on top and the narrowest range on bottom. Decision tree analysis is useful when we have multiple courses of action from which we have to select. This uses a concept called expected monetary value, which is a formula represented as probability times impact. We could also use simulations, such as a Monte Carlo analysis, which is a random iterative computer simulation. After entering in a range of expected outcomes, the computer will go ahead and select them randomly and offer a probabilistic distribution that could show us the likelihood of any one of those outcomes occurring. And finally, we have our influence diagrams, which show the relationship between variables and their potential outcomes. Here we see an example of an influence diagram and a tornado diagram. Within the influence diagram, we see that attending a PMP bootcamp does influence your PMBOK guide competency and also your exam taking tactics. If you study hard, this will also influence your PMBOK guide competency and your ability to be successful in the exam. PMBOK guide competency and exam taking tactics also have an influence on your ability to be successful in your exam. The tornado diagram shows the amount of risk going from left to right being a threat to an opportunity. So for example, with the human resource risk, we may have decided to go with a lower skill level than we normally do of our practitioners and have the possibility of seizing an opportunity that could lead to cost savings. However, we also introduce a threat that due to this lower skill level, we may have a significant amount of rework or training expenses incurred. Here we see a table of 4 risks that we are about to quantitatively analyze. These risks will be calculated using expected monetary value. Expected monetary value does require risk neutrality. If we do not have risk neutrality, then this formula does not work. The first risk is a delay in receiving parts. There's a 50% chance that this should occur, and if it should, then there's a negative $75,000 impact. So multiplying 50% times 75,000 gives us an expected monetary value of negative $37,500. There's another threat that the parts will not be correct, and there's a 30% chance that we will incur a $100,000 impact, which would mean a $30,000 expected monetary value. If there's a design defect, then we will incur an $8,000 impact, and there's a 10% probability of this occurring, which could be an $800 expected monetary value. But finally, we have an opportunity that if we have a sooner delivery to market, we could get $10,000, and there's a 40% chance of this occurring, which would give us a $4,000 expected monetary value. To determine the total expected monetary value, we will add together the positive and negative values, and it will give us $64,300. This is the amount of money that we would add in the form of contingency reserves to the cost estimates, which make up the cost baseline. The reason EMV requires risk neutrality, if we look at these various risks, if somebody is risk averse, they would look at this and say, well, if there's a 50% chance that there will be a delay and a 30% chance that the parts are not correct, why don't we just change suppliers? Now, at this point, we're no longer risk neutral. We're going to go ahead and select a different risk response strategy. We're going to select avoid. We will change something about the project to eliminate this threat. At the same time, we cannot be risk seeking. If we were risk seeking, then a stakeholder might say to you, well, why is there only a 40% probability that we're going to have a sooner delivery to market? Is there something about the project that we can change to ensure that it happens or at least increase the probability? And now we'll be talking about risk response strategies of exploit or enhance. Now we're going to take a look at a decision tree. The basic scenario is that our organization decided that it needs a new corporate headquarters. We have two options. We can either build a new structure or upgrade an existing one. Either way, we're thinking that in about 5 years, we're going to have to sell this structure and move on to something larger. Depending on how strong the market is, will determine the selling price at that point. If we begin by building, then we are going to have an initial investment of $120 million. So we are going to start out with negative $120 million. There'll be a 60% chance that there's a strong market, so we'd be able to sell the building for $200 million. But if it's a weak market, then we'd only be able to sell it for $90 million. One very important concept about a decision tree that we do have to point out here, every branch must have a total of 100% accounted for. So there's no possible way of saying there's a 60% chance of strong and a 20% chance of weak and 20% unaccounted for. If we take that $200 million and subtract the initial $120 million investment, then we actually have an $80 million impact. So if we take that 60% probability and multiply by the $80 million impact, we end up with an expected monetary value of $48 million. Now, if we have a weak market, the $90 million profit, we'd still have to take away the $120 million initial investment. So there's a 40% chance of a $30 million loss. So the expected monetary value would be negative $12 million. The expected monetary value of this branch of the decision tree totals $36 million. If we decide to upgrade an existing structure, that initial investment of $50 million is significantly less, and we're going to assume that it's not going to have any type of impact on the probability for a strong or weak market. If there is a strong market, we'll be able to sell for about $120 million. And if we subtract that $50 million, we have about a $70 million profit. There's a 60% chance of that $70 million profit, which means an expected monetary value of $42 million. There's a 40% chance of a weak market, which would mean a $60 million profit. We still have to subtract our $50 million initial investment, which means an overall profit of $10 million. So 40% of $10 million is a $4 million profit. Adding together the two possibilities here, the expected monetary value of this branch of the decision tree is $46 million. So which one should we choose? From a risk-neutral perspective, we should choose to upgrade. This is based upon the fact that the branch has a higher expected monetary value. Again, just to reiterate the point that risk neutrality is necessary, if we had a risk-seeking stakeholder, they might point out the fact that you could stand to make $10 million more if there is a strong market by building. The outputs from this process include project documents updates, specifically the risk report. Updating the risk report could include information from the assessment of overall project risk exposure, the chances of project success, which could be displayed numerically as a percentage probability of occurrence, and the degree of inherent variability. The update could also include information from a detailed probabilistic analysis. This analysis could be displayed as an S-curve, a tornado diagram, a criticality analysis, or further information about the amount of contingency reserves that are necessary to provide a specific level of confidence, the identification of individual risks or other sources, and the major drivers of overall project risk. We can have a newly prioritized list of quantified individual risk now that we have established expected monetary value. Trends in quantitative risk analysis results. This is typically done throughout the life cycle at a frequency determined as part of that risk management plan. This is where we can kind of check our work and see whether or not we're effective in our quantitative analysis. Recommended risk responses. Within the risk report, now that we have more information from quantitative risk analysis, we may have some ideas about effective risk response strategies that should be implemented as part of the follow-on processes in this knowledge area. Perform quantitative risk analysis, learning assessment. Describe the purpose of this process in your own words. This process analyzes the combined effect of identified individual project risk and other sources of uncertainty on the overall project objectives. Must this process always be performed for every risk in order to develop risk responses? No, this process need not always be done to develop an effective response, and it is worth pointing out here, for exam purposes, anytime you see definites such as every risk, it should at least be a red flag to read the question once more, a little bit slower. In what ways might we quantify the various potential risk impacts? It could be quantified monetarily, or we might say that there is a 50% chance of finishing on schedule, or that our schedule range is from 120 to 140 days. When, if ever, should we repeat this process? The process should be repeated after the risk response has been implemented to ensure the risk has been properly addressed. If we have one positive risk and one negative risk, how do we determine the combined expected monetary value? We would add together the positive and negative risks for the expected monetary value purposes. The results of a sensitivity analysis are displayed in a tornado diagram.